My name is Michael Wytock. I'm the CEO at Coshx Labs. Coshx is a distributed software consultancy based out of Charlottesville, Virginia. I'm local to New York. The talk today is entitled Performant Queries on Highly Connected, Exponentially Growing Data. There's some contact information here. Before we kind of get into the weeds of things, I want to give a big acknowledgement to one of our clients and partners, MCAM International. A lot of the domain-specific topics that I'll talk about today are coming from work that we did with them. They've graciously allowed us to give a little bit of insight to all of you about how their business runs and some of the work that we did in partnership with them to help it run more smoothly. MCAM is in the business of intellectual property evaluation, so they assign value to intellectual property. They also run a fund called the IQ 100. You can trade on this fund. It tracks innovation. Coshx Labs, as I mentioned before, is a software consultancy based out of Charlottesville. MCAM also based out of Charlottesville. Here's kind of an outline for the talk today. The first half is basically a business case study. I'll be talking a little bit about some of the work that we did alongside of MCAM. And it'll lay the foundation for understanding some of the problems that we had to overcome for the kind of technical case study portion of the talk. So getting to know patents a little bit. Start off with a bit of a definition of what a patent is. A patent is a government-conferred right to exclude others from making, using, selling an invention for a specified period of time. So it's a little bit of a complex idea to kind of exclude people from making some kind of invention. But the initial reason for patents was so that there'd be an encouragement for people to actually share these inventions with the public. So by getting this exclusive right to it, you're going to be encouraged to actually make that available to everyone to see. But there's a lot of complications when you start tracking the actual data underneath patents. If you think of other types of documents, such as academic papers that have citations, those citations are going to be from one document that exists kind of holistically from its inception throughout its life. That document doesn't change at like a 10-year time frame afterwards. But patents are a little bit different than that. There's a life cycle to patents, and there's lots of filings that go through. And they all kind of capture this one single invention, even though there could be many documents associated with them. So in the United States, if you had an application for a patent, you'd file that with the US Patent and Trademark Office. And then for roughly 20 years from that filing date, as long as you keep up with all of the prescribed paperwork, you would have that exclusive protection that that patent offers. So we would start off with this application, and then at some point, there's paperwork that's due to turn that into a granted patent. Each of these patents, or patent documents, I should say, are different documents. And those different documents will have different document numbers, and they can change over time. And then legal actions can also be taken on these documents. So for example, if an exceedingly broad invention was brought to bear, that invention may, through some kind of legal action, be deemed to need to be split up. So we may create two separate patents that came from some court action. And we get this fracturing of what was once a single document at the start. But we can also seek for international equivalencies. And this is increasingly important today with global economies tied together. And it's getting a lot easier to seek these equivalencies as well. So if you're in the United States and you want to seek protections in, say, Japan for your patent, usually there has to be a treaty between those two countries that sort of smooths the way for these types of protections. You can go to Japan and say, hey, here's my patent. It's filed with the US Patent and Trademark Office. I'd like an equivalent patent in Japan. There's a procedure and more paperwork that goes through it. And then Japan has their own process, similar to this one, where you may create multiple documents out of the equivalency process. So at the end of the day, we end up with not really just one document for an invention or piece of intellectual property, but a smattering of documents. And we call this a patent family. The European Patent Office has taken great lengths to try and track these families. And obviously that problem is a little more transparent in Europe, where the Eurozone creates many different economies that are tied together. Whereas in the United States, it's a little bit more insulated, viewing the United States economy and the government's control of that economy as sort of the most important thing. But with those international equivalencies, you can now get your single patent sort of shot out to 5, 10, 15 different countries. And increasingly, companies are doing so. So this is an example of an American patent. The American patent that we're looking at here is for a golf putter. They usually have these really involved names for what's kind of an everyday item. So this one is golf putter head with top and bottom components made of materials having different densities. That's pretty standard as far as how these things are worded. And I've pulled out a couple of pieces of data that were of interest to us. Obviously, title, filing date, the granting date, patent number. That's important. You want to know if this patent's in force or not. If too much time has gone by, it won't be. And then there's really two pieces of data that I think are going to be really important for kind of the technical part of this talk. The first is this idea of an assignee. Looks like assignee, but everyone in the field I've talked to has pronounced it assignee. And then citations. So assignees are the entities to which that exclusivity is going to be granted. There can be multiple of them. Sometimes it's the inventor. In this case, it's not. We have an inventor named David Jones here. He maybe worked for Karsten Manufacturing Corporation. We don't know. But that exclusivity is going to be granted to Karsten. And then there's citations. And citations are probably very familiar to everyone in the room. There's related works that maybe you're building off of that you want to give credit to, or maybe you're forced to give credit to by someone who reviews the patent. And those citations are documents here in the United States in this case, and then foreign patent documents in this case. So you can cite across different countries, and that's obviously important for enforcement reasons as well. So kind of coming back to what the goal of all this really was, when we were approached by MCAM, this is kind of the way things were structured. We're saying we want to improve the performance of this existing algorithm that we have that assesses the value of a patent portfolio. There's a couple of little things I want to unpack about that. Performance. So, okay, what was the performance before? They're mostly concerned with, say, the top 100 largest publicly traded companies in the United States. For companies kind of in the middle of that range, say around 50, it was taking about a day, maybe a little longer, to crunch those portfolios of patents and to assess the value on them. There's also an existing algorithm. That existing algorithm was a Java client that was accessing a relational database. And there's some patterns, and I'll get into this a little bit, that algorithm would be checking against to do this valuation. Those patterns would have scores associated with them. Those scores would be used to value the patents. Then there's this idea of value. So like, what is a valuable patent? There's lots of ways we can consider this. MCAM has multiple ways, but by and large, our analysis was mostly concerned with citations. So in a citation network that says something, and we were talking earlier today in the keynote about those relationships, giving information about the data that we have in a way that something that lives on top of a node, for example, can't. And this idea of value through relationships, in this case citations, was really important. So by and large, value equals citation relationships. If I cite you, what does that mean? If I cite you and you cite someone else, what does that mean? If I don't cite you and maybe I should have, what does that mean? And then we are also talking about patent portfolios here. So we've talked a lot about individual patents, a single invention, but large companies own many different patents, and they kind of compose a portfolio of intellectual property. And I'm sure in the news people have been aware of either legal battles surrounding this or companies that are acquired generally for that intellectual property, either because it's a threat to them or because they could leverage it against another company. And we have to think about all of this in aggregate. So the key point here being that there was lots of aggregation that would have to go on. We have a lot of different documents need to be aggregated into one. You have lots of different companies that go by different names, and there's nothing that de-aliases all of those names, so they need to be aggregated into one company. And then we have multiple different patents that could be the same in a lot of different companies. They kind of need to be aggregated into one. And then we have multiple patents or inventions that this company rightfully holds, and they need to be aggregated into a portfolio that can be analyzed. So this talk bills as talking about highly connected and exponentially growing data. I want to be able to quantify that for you a little bit. So in our database, we ended up with about 140 million nodes, 100 million or so of which were patents themselves. The other 40 million were assignees. The colors on here are roughly correspondent to this snapshot of the graph. So kind of around the outside here, we've got lots of little assignees that are attached to certain patents. And then those individual patents are going to be assigned to companies. This will be blown up a little bit on the next slide. But right here in the center is Walmart, really one of the aliases that represents Walmart. And then we have 5 patents that are all assigned to Walmart here. We also have a couple of citations that are showing. So we're actually showing the one-hop space in terms of these citations surrounding these 5 Walmart patents. So this one's got 4 citations coming off of it, so on and so forth. The purple nodes, in case you're wondering, aren't really relevant to this discussion. They're a way we were aggregating some of these names for other companies and selecting ones that we were most interested in. So if these companies here are not of interest to our analysis, we may throw the data away. And this is kind of a sentinel about whether or not we should do that. The relationships, as I mentioned, there's really 2 main types of relationships: citation relationships, which are going to attach one of these patent documents to a assignee, and then, an assignment relationship. We'll be taking the patent document and attaching it to an assignee. And then there's citation relationships between all of these patent documents. And as far as properties go, we had about 900 million properties. Those properties are things like expiration date, issue date. We kept a pretty sparse graph in terms of how much data we were putting on these properties. We knew that we were going to be studying citation relationships. We didn't pull in the whole kit and caboodle. There wasn't free text sitting there on each of these patents. So here we are kind of blowing things up a little bit. You can see that Walmart patent here in the center. It's assignments to these 5 patents. And then you kind of have that context from the prior slide about what this one-hop space, or what we'll refer to as this one-hop space, looks like. We would often be concerned with, say, the 2-hop space around a patent. So we want to know who your patents cite and who they cite as well. It's a little bit difficult to visualize that. So it's kind of why this slide here just shows that one-hop space. But if you can imagine pushing that out one frontier further and then pulling in all of the assignees that would be associated there, you get an idea for how much you can return from one of these queries. So how highly connected are these data? If you're looking at Apple, and Apple is kind of middle of the road in terms of patents held, raw number of patents held. When we run a query here matching for Apple, we end up with about 60,000 patents. And the citations from Apple, though, balloons quite a bit to over 1 million patents, 1.4 million or so. It's about a factor of 20 increase. So we can tell here that on average, these Apple patents are citing 20 other patents. And if we're looking at the 2-hop space, we extend that one step further, we're ending up with over 200 million patents. And if you recall from 2 slides back, there's only 100 million patents in the entire data set. So how are we returning all of these patents? Well, we're really returning the pathways to these patents. And since we have all these citations, we're ending up returning a lot more data than we thought we would initially return. And this is one of the big issues that was happening with this relational database. As we're doing these joins on the data, we're returning tons of data. And every time you want to go one step further, you're ballooning the amount of data that you have to work through. So just kind of like a disclaimer about Apple, Apple is actually a fairly highly connected portfolio. But increasingly in recent years, lots of companies are issuing lots of patents each year. So I think those are kind of changing. Apple being kind of a young company in terms of some of the others that we would analyze in this analysis, they're increasing at a really quick rate. Speaking of which, how quickly are patent issuances growing? Here we have the number of patents by year. And you can see there's kind of this curious little plateau that's happening. There's about 4 million per year being issued right now. And then if you kind of change the analysis a little bit and look exclusively at patent families, you start to see a bit of a different picture. When we kind of reduce all of those down, we're seeing that we're actually getting a lot of independent patent families issued each year. And it's clearly on the rise in recent years. Looking at citations, got about 15 million citations per year, a little bit more than that in recent years. Again, appears to kind of be plateauing a little bit. But if you look at some of the portfolios that we were interested in with these very large companies, you can see that they're citing a lot more people in their patents as well. And sometimes it can happen for a variety of reasons, but you need to cover yourself on a legal basis, and that's one of the reasons why you may be doing this. So getting into some of the algorithmic challenges that we needed to tackle. And these are kind of handed to us a little bit from the prior analysis that was being done. We wanted to stay true to the analysis that MCAM had already once we did this implementation in a graph, and then maybe offer some improvements where we could. So this kind of coral colored node here, I'm going to call that kind of our subject patent. You would imagine that a company of interest, say Walmart, owns this patent. And we want to know things about it. What's its value? There's kind of a pathfinding problem that we'd have. And in this pathfinding problem, we'd want to find all of these subject patents that are owned by, say, Walmart. So we'd look that up. And then once we had all of them, we would focus on a single subject patent. And we'd want to know about its citation network. In this case, we're talking about a two-hop space, one citation, two citations. And then we would want to find all of these cited patents assignees as well. So there's these kind of hidden assignments that we would want to know about. Who owns these patents? So that's kind of the pathfinding problem. It's common to a lot of graph issues. And then pattern matching, which is another really common graph problem. When we look at one of these citation patterns, say a forward citation and then another forward citation here, we would have rules about what the score should be assessed for that type of citation pattern. We have to check against a number of these rules for these patterns. So we do lots of pattern matching on a single pathway. So when we were talking before about those 200 million pathways that we were retrieving for Apple, we would then, for every single one of those pathways, do somewhere around like 10 pattern matches to see whether or not those scores would be good or bad, indicating good or bad things about the quality of the patent. And then we would have to aggregate and serialize a lot of data. So as mentioned before, we're dealing with a portfolio here, not an individual patent. So once we got a score for, say, like an individual patent, subject patent A, we would then have to aggregate all of the other Walmart patents together and get some kind of intelligible score out of it. This slide is kind of showing where the data was in a relational database before we got a hold of it, just to kind of show where we had to move from there. If you were to do this type of path analysis to retrieve these paths in the relational database, something like this would happen. If we were interested in this US 9 million patent, we would look it up in this CITER column of our database. I would use the global index in the database to do that. And then if we wanted to go 2 hops out, we would have to get another citation. So we'd do a self-join on this table. For this first citation, let's say we don't have a JP citation. It just cites no one somehow. We'll dead end there. That's fine. But for this US 9.4 patent, maybe we have 2 more. So when we do this join, there's another global index lookup that has to be done. And we get something that looks like this. And right now, what we have is a table. It's a joined table that is going to have 2 forward citations, which is great, except we're interested in backward citations as well, forward citations and then backward citations, then forward citations, et cetera, all those permutations. So you'd have to do these joins multiple different ways to figure out where these paths are. And it's a pain. So we were kind of thinking about this problem. We were like, well, we should try a graph database, see what works. So these are kind of the reasons that we decided that it would be worthwhile to look at a graph database. We get index-free adjacency instead of these global index lookups. So if you're not aware of that term, the idea is really pretty simple, that if I'm sitting here at one node, I have references to everyone who's 1 hop away from me. So I just go there. I don't have to look up in this huge table with a global index to get there. There's also undirected queries. So we're not stuck with this directional querying or storing data in multiple different ways. Like maybe we store the undirected citation space, but then we have to know whether we're in the undirected or the directed and store that data in extra columns and know that. So it's a little bit more natural, and that kind of speaks to the last point here, that this native graph model, instead of the tabular graph model, you don't have to go back and change your data afterwards if you decide that, like, you know what, the 3-hop space is really important. We would have to go through a huge batch job to change our database structure, perhaps going back here to add extra columns. If we needed performance search on this, we would have to maybe do a lot of compute when we started storing the data to get it in the right format. So in moving to Neo4j, we kind of had 3 stages in our implementation. The first stage, we were using a parallelized Python client and hitting the Neo4j database. Did the same thing in the second, and then in the third one, we finally went full in on a stored procedure. And the thing that's kind of interesting about the changes that we made are how we parallelized in the first 2, and then where we were doing our aggregation. So the aggregation locale for the very first kind of rough cut version of everything was just files on disk. We were like, all right, let's look up these patterns, score them, throw them out on the disk. And then for the second one, we were like, well, some indexing might be kind of nice. Like these files that just have a bunch of data sitting here on the disk take forever to aggregate. So we've got a database next to us. Why don't we just throw them on the database? And then the final one, like let's use all of the niceties of being inside of a Turing-complete language, working within Java, use a stored procedure, use the memory to do our work. So in this first iteration, we were doing parallel Cypher queries with disk writes, so writing back to files on disk. Down here at the bottom, kind of attempting to show that for a single patent, we broke these up to really pretty granular queries. We would match, like maybe say 2 patterns on those pathways in the first thread, and then we would parallelize across those patterns. We were like, well, this will be really good because these queries will be super lightweight, and we won't end up with a situation where we can't get this work done and we lock up a thread with some really long query. It ended up being a little too easy for the graph database. And Python with the global interpreter lock, if you're familiar with it, dealing with multi-threading inside of Python can be a little bit messy. And with our thread pool and then the connection pool to our database, there was a lot of data being sent back and forth, lots of queries initiating and then ending in short time frames, that it became a really chaotic system. For small portfolios, it worked pretty well. As you got bigger, there were just way too many threads being spun up and then, again, later being used again. And then the worst part of it is that our results weren't indexed. We would just get all the data back and then dump them out into these files and then have to aggregate them later. So the lesson here was do more in a query before you start serializing it. So the next time around, we're like, OK, well, let's do 2 things differently. Let's put all of those pattern matches for a single patent in a single thread. So they're all sitting there together. And then the next thread will just be a totally different patent within the same portfolio. So then we know that we have everything about that one patent already completed. It made for more demanding queries. And in truth, we had to kind of jerry-rig this system where towards the end, if we were running into these like really gnarly queries, that we would kind of put them off, and we'd kill the query, we'd have a timeout, and then dedicate a single thread to these really bad ones towards the end. And that was because of memory issues. For some of the really large patents, they have these pathological citation pathways, oftentimes self-citing or citing other patents within the same portfolio. There's a lot that could be said about them. But when you'd run into them, you would know because these queries would just seem to be orders of magnitude longer than others. There's also lower input-output cost because we were starting to write to Neo4j. So as I said before, we were saying, why don't we just use the database as a scratch pad? I mean, it's there. We're already inside of it. We don't have to pull the data back out to a file, write it, read it again, and then do the aggregation in memory in some other paradigm. And there's good and bad things about that. But in general, if you need to, consider using Neo4j as a scratch pad. If you're not really sure how you're going to then pull this data together, and you know you have a lot of it, you might as well dump it somewhere where you'd be able to get it out quickly again and pivot if you need to. So that's what we did here. And we had less of the input-output costs that we had before. Before kind of talking about the stored procedures and how those were used, there are also 2 other kind of key little optimizations that may be useful in some of your own graph queries. The first one I'm calling dynamic label setting. It's also kind of like creating a forbidden fence within your queries. It's a really simple idea. So for us, we're talking about pathways, and with these pathways, at the outset, we could tell all of the patents owned by Walmart fairly easily. Right now, they're represented by a relationship, and there's reasons for that instead of a label on those nodes. But what we would do when we would start running, say, Walmart as a portfolio, is we'd go find all of the nodes that were assigned to Walmart, and we'd go put a label on them saying, like, these are the Walmart nodes. And when you have thousands, sometimes millions of nodes that are going to fit that query, you'll save yourself some pathfinding a little bit later if you know you don't care about these patents in the same way that you do the other patents. So we limit our search space by doing this, and that's really the key idea. Anything you can do to limit your search space is going to be useful. In Cypher, with the query planner, sometimes you need to get a little bit creative with the ways in which you limit that search space, using labels and things like that. So this is a really simple query that basically just takes a label and says, return the ones that don't have it. But something akin to that is what we would do. So we would say, hey, A and C, they're both assigned to Walmart. And then we'd basically pull C out once we were able to hop to A. We'd say, hey, we know that C's here and it's also assigned to Walmart. We can just dump everything that has to do with C out of this and stop traversing that pathway. We don't want to return it. And then database warm-ups. If you haven't run into this issue, one of a couple things is probably true. Either your database is always on, maybe it's a little bit smaller and there's not a need to pull everything into page cache immediately. But if you're dealing with databases that aren't always on, so for us, we were doing a lot of batch jobs. We'd pull in a bunch of patent data, run it on these quarterly changes that happened. We would have a lot of uncached data sitting around. There's a tremendous performance difference between a cold and a warm database. And it's not always obvious exactly why this is happening. But the idea is that if you don't run the warm-up, your first queries will for you. And they won't necessarily do it in a way that is going to help out with the query performance. So there's an APOC call to do this. APOC warm-up run true. If you're not familiar with APOC, basically grab a jar file, you put it in the correct location, you reference it from a config file. Now you have a bunch of these stored procedures you can use. One really important and at the time underdocumented parameter for APOC warmups is pulling properties into the graph. This true parameter pulls those properties into the page cache. It changes things dramatically if you're looking at any property on a relationship or a node during those early queries. Before warming up, a small portfolio, like the smallest portfolio we would run, the Progressive Insurance Company, took about 15 minutes. Afterwards, it was about 50 seconds or so. And the only thing we did to get that was using this true parameter. We were warming up before. We just weren't pulling properties in. And for us, properties were used for things like, is this patent expired? Check on the node. If that date is before this date, then it is. So then Java stored procedures, what's the deal there? Why should you do that? Or maybe you shouldn't. So for us, there was no need to manage threads anymore. So that was nice. And then we could do some imperative rather than declarative graph traversals. So that was also becoming pretty nice. We started doing cute things like you saw before with that dynamic label setting. And we were starting to realize that with the way the algorithm had been written before, there were a lot of conditionals in this algorithm. And we were starting to put them into case statements inside of Cypher. Case statements in Cypher are ugly. We were also starting to aggregate things inside of Cypher. So we were doing collects and then unwinds and then collects again and then with statements as this. And it was like turning into like modules. And then you start thinking to yourself like, oh, it'd be pretty nice if we just put a function around this part and then returned it to this other function that does the next part, which is good. But you start losing performance if you have to separate out to separate queries for each of those things. If you know what this traversal is, and it's quite a custom traversal, you probably should be thinking about using a stored procedure. We also got to aggregate things in memory now. Obviously, we were doing that before within Cypher, but we just didn't have very much control over the data structures that were available to us. So in kind of giving a little bit more of a comparison between Cypher and then stored procedures, I will note that at the start of it, my colleague and I were thinking to ourselves, like, this sounds like it's going to be a mess. Like, we're going to be in there, like, munging around with, like, Neo4j, like, implementations of things, like, trying to find the correct interface to call. But the community was super helpful. To name people by name, Max DeMarzi, hanging out in the Slack, basically just like shot us off a jar file that was like, here you go, everything's kind of hooked up. You'll change a couple of things here and there to meet your schema, but then you can just traverse this graph in an imperative fashion in a really intelligible way, using dumb things like for loops. So in Cypher, you're ending up with a declarative query language, which is great because most of the optimization is done for you. But if you know you're in a situation where you can avoid a lot of search, if you do it in a custom fashion, perhaps you actually want an imperative search. So you may find that that would be a good need for your stored procedure. Data types. In Cypher, you get basically maps and lists. There's strings, obviously, as well. But in Java, you get whatever you need. There's native data types throughout Java. You can use those. For conditionals, it's kind of hard to do conditionals inside of Cypher. And inside of Java, it's as easy as it would be if you're writing any other program. And then Cypher oftentimes defaults to a depth-first search when you're trying to go find nodes in a graph. At times, you want to escape that and do something conditional, maybe a breadth-first search or a variation of it in order to optimize the searching that you're doing. So I'm not really trying to like overload by throwing a bunch of code up here. I kind of want to just show how simple it really ends up being. Basically, here's a big import statement. The important parts up here are going to be you're going to have to set your own kind of like schema. So you'll put in the labels that you have and the relationship types that you have. Makes Neo4j aware of it. And then there's this map result. So you have to pull in the type of result that you want to return. So we're aware that in Cypher, you can return maps. This just means that, OK, we'll be able to return this query as a map inside of Cypher. And then down here, we'd pull in the Neo4j classes that are necessary. You see things like this graph database service. That's a contextual thing that's needed. But then others are going to be very familiar: nodes, relationships, directions. And then this is kind of a mocked up version of finding two-hop space. So we would use these decorators and then call in this two-hop space function, passing in our case, a patent number. So we get a pretty nice interface when you're inside of Cypher. You're just like, my function, two-hop space, and then parens, and then here's the number that I want to look up. And then you'd be using, obviously, the parameters that get passed in here to use some of these functions that we saw, or classes, I should say, that we saw on the previous slide for finding a node, finding the directionality in a relationship from that node, conditionally, maybe tabulating some numbers based on that. And then at the end of the day, you can return this map result and stream those back out through Neo4j. So in conclusion, for highly connected and quickly growing data, there's a couple of things that you should keep in mind. Warm up your database, warm up with properties. I believe right before I was preparing this talk, I saw that the interface has changed again for that APOC warm up. There's a couple of other parameters. There's maybe more things that we can warm up in page cache. I'd be curious to chat more about that. Narrow your search results as much as you can. One way of doing that, or excuse me, your search space, is with labels. You can dynamically set labels and then get rid of them. You can use your graph database as a scratch pad. And then consider stored procedures if you run into any of these issues. If you know that imperative programming is going to limit your search space tremendously, you may be able to get more performance than Cypher is going to offer you. And if Cypher queries are becoming unwieldy and the interface is nasty, the cost isn't super high to implementing the stored procedure. So doing so will be really nice for the usability of your code in the future. And then if your queries are generating lots of data and you know you're going to have to aggregate a lot of that data, then that's another great use case for using these stored procedures. You'll be able to use those common language constructs inside of Java to be able to do these aggregations as opposed to trying to return data to some intermediary source, write that to disk, something like that. So that concludes the talk. Be in touch. I'll be kind of in the hall afterwards. I think we may have a couple of moments for questions right now. And then my contact information is here. So I can try and give the microphone out. May have time for like a single question, maybe two. Yeah. Here. I think they'll be able to hear you on the video if you use the mic.
So my question was, when you defined all of your requirements to create your graph, what was the depth of your unique types of nodes? You said patterns, you said assignees, and then you had citations. Were there's 3 nodes in overall, or like how did?
Yeah, that was it. So we just had those types. We had a bunch of different labels for these different corporations because we would sometimes be doing things like looking at a ticker symbol, which doesn't actually translate directly to a single company's name. Okay. So we'd have other labels out there, but as far as node types are concerned, those are really the main ones.
I see. And so the query performance, when did you really hit the wall? Like, I know when the data grows, when you start creating data, you're like good for 1 million, and then you start growing, and then when did you hit the wall, and what did you do at that time?
Yeah, so with the relational database, some really, I would say, like difficult parameters around their work were those self-joins happening on that table, and that was already an issue. So like as of probably 3 years ago, that was a problem. And so there were like cute things that were being done to sort of like cache that stuff and maybe create a different wider table to store that data. For us, the 3 things that kind of changed performance drastically throughout the way were moving from a bunch of Python processes to that stored procedure. That was an independent thing that caused a huge performance increase because we were going back and forth with a lot of different queries. There's overhead to doing those queries. And then the other thing was definitely the way in which we were doing the aggregation piece on it. Storing that stuff in an indexed fashion was useful when we had to do that. The final thing I think that was very surprising to us, we were sitting there getting the same performance we had out of the relational database, was warming our database up. If you're leaving your database on all the time, you're probably okay. But we were like leaving off like this very large EC2 instance and then spinning it back up again like once a quarter to run these things. We would do a whole new import because there's so many amendments that happen in a quarter for patents that you have a completely different data set. And it doesn't make sense to just change the nodes that you have. You just want to pull everything new. And then nothing's in memory. So then you'd have to pull it into memory. And those properties they were extraordinarily helpful in increasing performance. Yeah, I think there was maybe one other over here. Yeah.
You just mentioned that use a Cypher. It's very difficult to run a conditional query. For me, it's not so difficult. Do you have some real case to show to us? Why difficult?
Yeah, so for us, we had somewhat arbitrary, handed to us by the domain experts, patterns that we would search through. So we would end up with, like, if you have traversed this far down a path, and this patent is owned by a certain type of assignee, do this, and then change the way you do your search later based on it. So for those conditionals, we were ending up with just like really disgusting code, trying to use, say, like case statements and stuff to get through that. So for a single pathway, we'd be checking like 5 or 6 things and then changing the way in which we would do subsequent queries based on it, if that makes sense. So there are just lots of them, so there are lots of different pathways, and you ended up with basically like for and if statements inside of your Cypher code. Yeah. Yeah. Yeah, I think we'll make this last one.
How many nodes and relationships do you have in database? How much it takes in file system? And how big is the heap size on your server?
Got it. So nodes, about 140 million. Relationships, close to 1 billion. Disk size, 60 or so gigabytes. Yeah, and then heap size is approaching that. So we would be getting instances that were somewhere around like 60 or 40 gigabytes of heap size, if I recall correctly. It's been a while since I've tuned it. If you have any other questions, you can see me after the talk. I think it's time for lunch, so enjoy the lunch. Thanks so much for your attention. Yeah.